there are three basic types of probability that we classify them into. Classical, and classical is what we always call theoretical. I always called it theoretical. It could be called classical. This is by theory. This is by your theory. You flip a coin a zillion thousand times. The heads is always 1/2. The tails probability is always 1/2 on a fair coin. You have a 6-sided die. Each side has a probability of 1/6 on a fair die. And you see that word fair used a lot because sometimes dies are weighted, coins are weighted. So you see the word fair used a bit. Now, we find our probability by taking the number of times it happened over the number of outcomes that are possible. Okay, these will not change. They remain fixed all the time. So, example of classical or theoretical probabilities. You roll a die, a 6-sided die. If it helps you, put these out like this. You roll a die. So the probability that you get a 3, and we write it like this. The probability of a 3 is how many total outcomes do you have? 6. How many of them are 3? 1. So we write our probabilities like this. We usually keep them in fraction form. Unless we're doing like work calculations, then we'll use a decimal. The probability of rolling a 7 is what? 0. This is your impossible. I don't have a 7. This is your impossible. The probability of rolling a number less than 5. How many of those are less than 5? 4. So I have 4 that are less than 5 out of 6 choices. If you want, you can reduce them down. Don't reduce them to the end just in case you're adding or doing something else with them. Alright, so these are good examples of classical probabilities. They will not change. They will be fixed all the time. Okay. Standard deck of cards. How many suits in the deck? 4. Okay, let's talk your cards. 4 suits. What are they? So, do we notice that half the deck is red, half the deck is black? Okay, how many cards? Marissa, you want to move up one seat? Just move up one seat. Move up one seat. How many cards do I have altogether in your deck? 13. There are 52 cards altogether. Each suit has 13. This is 1/4 of your deck. How many face cards in hearts? 3. What are they? The king, the queen, and the jack. These are face cards. The ace is considered a 1. Okay, the ace is considered a 1. We don't count the jokers unless they tell us to. So normally we have 52 cards in a deck, and we don't really count our jokers. Now, what is the probability, therefore, of selecting a 9 of clubs? How many 9 of clubs are in your whole deck? 1. How many cards in your deck? 52. What is the probability of selecting a heart? 13 over 52, or 1/4 of your deck is hearts, right? So you can write that either way. Or, it's the same as 1/4. What is the probability of selecting a diamond, a heart, a club, or a spade? 1. They gave you a trick question. Your diamond, your heart, your club, or a spade. It's always going to happen. That's all you have in your deck. But we're not counting jokers. We only work with the standard deck of 52. So these are the kind of questions they're going to ask. So know these. There are 4 suits. Each suit contains 13 cards. 3 of them are face cards. Then 1 through 10 are regular cards. So the ace is a 1. And then your jack, queen, and king are your face cards. If they add in the jokers, they will tell you. And then it will change your total in your card deck. So these are things that we're going to look at. Okay. And if you struggle when we do cards, I have a couple of nice sheets that have card decks on them, and that'll help you out. Okay, empirical. I like to call this one they call it your statistical. It's also called your experimental. Experimental because this is where you do the experiment. You flip a coin 10 times. You flip a coin 30 times. You roll a dice 100 times. This is your experimental. And your experimental does not necessarily have to match your theoretical. The idea is that the more you do it, the closer you will get to your theoretical. But your experimental, you can flip a coin 10 times and get 10 heads. And still the probability of flipping the coin again is 1/2. That's not going to change. Your theoretical is not going to change. So if we flip coins and we roll dice and we do these millions and millions of times, we get the closest we can to our probability, our theoretical probabilities. So again, you still do the frequency of your event over the total number of frequencies. If I have a coin and I flip it 100 times and I get 10 heads, then my probability of heads was 10 out of 100, or 1/10. Okay? And that can happen. Subjective probability has a little bit of difference in here. This is a little bit of your educated guesses and your estimates. This is called your gut feeling is in here. A little bit of your gut feeling, like what do you think about this? So a lot of it's like dependent on what else is going on. The weather. The weather is very subjective, and we talked about that on Friday. One weatherman could say probability of snow 40%. Another weatherman could say probability of snow probably like 10%. Because they look at the patterns, they look at all the theoretical probabilities, what has happened, what's supposed to happen theoretically, empirically what has happened when they see these results, and then they throw a little bit of their feeling in there. For as many times as I've seen this, I know I really have a good feeling that it's going to pass us. So they throw in their gut feeling into this. This is your subjectivity. That's a little bit harder to measure. So we have a company, and they're conducting an online survey of randomly selected individuals to determine how often they recycle. So far, 2,451 people have been surveyed. This frequency distribution shows the results of the survey. What is the problem, or what is the probability that the next person surveyed always recycles? What's the probability that the next person, based on this, we're going to use these numbers to forecast, to predict what's going to happen next? So what is the probability that the next person I survey always recycles? It's 1054 out of 2451. This is what I'm going to use to predict what's going to happen. Okay? And you throw it in your calculator. Easiest way to do this is probably going to be 3 decimals. When you're comparing large numbers like this, it's very difficult, to reduce it and then try to compare them, because some probably won't reduce anyway. But when you're kind of comparing them, if the denominators are not the same, then go to a decimal. It will make it a little easier. What is the probability that the next person I pick never recycles? 171 over 2451. Okay. Based on my distribution, I can predict what's going to happen next. I can forecast, predict. I can guess what the next person is going to do based on the results of this. Will I be right? Nope, because again, it's experimental. These are not theoretical. These are experimental. They will change with the next group of 2,400 people that I survey. Every time I do this, they will change. So this is called my empirical results. And I like to say experimental because that's your experiment that you do. Okay. An insurance company determines that in every 100 claims, 4 are fraudulent. What is the probability that the next claim the company processes will be fraudulent? 4 out of 100. What is the probability that the next claim the company processes will not be fraudulent? 96 out of 100. What case is that when we use the what's left? What's that called? Complement. That's your complement case. Okay? So we see a lot of probabilities going on here. Okay. A company is conducting a phone survey of randomly selected individuals to determine the ages of social networking site users. So far, 975 social networking site users have been surveyed. These are their results. Are these results theoretical or empirical? Empirical. Are they set in stone every time I survey 975? Will they always look like this? No, they're based on your experiments. So these are your empiricals. The frequency distribution that they show is over here. What is the probability that the next user surveyed is 23 to 35 years old? That's it. 312 over 975. Okay. What is the probability that the next person surveyed is 18 to 49 years old? You would add these guys up. You would total those over 975. Would they come up to? 726? 2. Thank you. More than half of your chart there, right? Okay. What is the probability that the next one I surveyed is not 65 or older? What's a very quick way to do that one? Michael.
975 minus 52 over 975.
Good. Use the complement case. It's everything but that one. Rather than add them all up, and in this case we didn't have to do too far because Jared already added up these. We could have just added one more to it, or we could use the complement case. Yes.
Wait, where did the 50
58. 975 minus 58 over 975. Is it 52 in the book?
No, you're right.
Oh. Okay. So we can use your complement case as well to have to do that. What is the probability that the next person will be a female? Can we tell from this?
No.
Nope, can't tell from that. What is the probability? Okay, we can do that one. Okay. Law of large numbers. Your law of large numbers says if you keep repeating over and over and over again, you will approach your theoretical probability. And sometimes, even though we do something a zillion times, it could still be off. But the larger the number of times we do it, the closer we will get. So let's look at example 8. Let's classify these into our 3 types of probabilities. Every time I touch this, it goes crazy. We have classical, which is your theoretical, empirical, your experimental, and subjective. So what type of probability is it that the probability you will get an A on your next test is 0.9 or 90%? You have 3 choices. Subjective, so why would we say subjective?
Are you going off of any data?
Well, give me your reason for saying subjective.
Different data.
Could that be your average? If it could be 2 things. If that's your current average, then the chances are you could get a 90 on your if that's what you're going based on. So they're forecasting based on your average. It could I make this into a subjective part? Subjective because I just get that good feeling that I'm going to do real well on this test? Subjective. I would probably go with the subjective just because even though your average is 90, does that mean you'll get a 90 on your next test? I could predict you'll probably do around 90, because that's what your average says, but this is probably more of a subjective question. But if you gave me a valid reason for it being empirical, I would kind of get the empirical part of it. It's kind of a little bit ambiguous, but I would go with the subjective part. The probability that a voter is chosen at random will be younger than 35 years old is, I kind of messed up that, years old, is 0.3 or 30%.
Empirical.
Empirical. Why would you say empirical?
If there's been studies on the amount of voters in past years.
Yeah, because of the recent studies of voters. Maybe in another 5 years I'll do a different group of, or next month I'll do a different group of people and study them. But this is based on the people that I have out there now. Is it going to be this way every year? Mm-mm. The probability of winning a 1,000 ticket raffle with one ticket is 1 out of 1,000.
Well, there's 3 examples that you put on the board, and there's 3 probabilities, so the probability
The probability that that's the theoretical, classical. Well, it could have been that we used 2. We didn't have to use all 3 different ones, right? But that is your classical or your theoretical. That one's not going to change. If there's 1,000 tickets and 1 winner, 1 out of 1,000. If there's 10 tickets and 1 winner, 1 out of 10. Is it the probability that I would win 1 out of 10? Probably a little less than that because I'm not a lucky person. But that's my subjective part. Okay, so we can go with subjective on this, kind of like your gut. I studied, I did well, I've been doing real well. If you kind of go based on your average, and I've had kids in the past say, well, what if my average is 90? Am I forecasting? Like, you're kind of forecasting. Okay, so based on previous counts, the probability of a salmon swimming successfully through a dam on the Columbia River is 85%. Is this an example of classical, empirical, or subjective probability? David, what would you say? Mm-hmm. Mm-hmm. What would you say, Michael?
based on previous counts, that data, so I would say statistical.
Statistical. Well, statistical being your empirical. Based on previous counts. Does that mean we'll be the same every time? It's just this is the number that we took in. This is what we found for this group. Okay. If it was based on the researchers' feeling of how a salmon behaves in different weather, then I would say it's subjective. But because it did have specific counts, I would go with the empirical statistical. Okay. And this is just to kind of review the rest of your probabilities. Your range of probability rule, your probabilities themselves go from 0 to 1, whether you're fractions, decimals, or percents from 0 to 100. There's no negative probabilities, ever. The sum of all your probabilities for an event equal to what? What do all your sums of your probabilities for one event equal? 1. So the complement, therefore, can do the 1 minus. If we don't want to add up all 4 things because we only want the 5th, or do the 1 minus. Or if we want the 4 when we don't want the 5th, do the 1 minus. And again, we looked at this before. I kind of did this before with you when we had the chart up. Okay? Now, sometimes, yes?
When you said the law of large numbers, you mean like the more times you test it, the empirical and the classical will most likely be alike?
It will approach the theoretical part, though. Yes, the classical part. It will approach it. I was hoping to do one today, but I didn't reset all the calculators, so hopefully tomorrow I'll do it. We flip coins. We flip them on the calculators. And so everybody will do it like 50 times. And we'll look at everybody's probabilities. Then we'll add all of ours together. So as we add them together, you should see it approach the 1/2. I mean, sometimes when you flip it 50 times, you can get like, some people can get 10 heads. It just happens. It's a random. It's all random the way it's generated. The calculator, I'm not sure if the calculator does it like they do their random number generators. So I'm going to have you flip it like a number of different times randomly first, and don't reset your calculator, because sometimes with like the table, it all goes from the same place. So I'm not sure if it does that with the flipping of the coin. So I'll just tell everybody to practice like maybe 10, 20, 30 times. Just, flip the coin a few times on the calculator and then start your count. And the calculator can make a table or a graph. We'll make a table, which will show you the probability of your heads. And the probability of tails is the same exact thing. So good question. So we're going to, hopefully tomorrow, I didn't reset all your calculators. I have the thing for it, but I didn't reset them all yet. All right, so let's take a look at, we did a tree diagram, and we did your fundamental part. So let's take a look at example 10. You're going to have to look in your book because it has a spinner on page 139 that we have to look at. We're going to toss a coin, and we're going to spin a spinner. Notice the spinner has all equal sections. So let me just show you something first. What is the probability of getting a 1 on this spinner? The spinner that I just drew. 1 what? 1/4. We have to separate these into equal parts. Whenever you figure your probabilities, they always have to be equal parts. So 1/4. What is the probability of getting a 3? 2/4 or 1/2. So you always have to make sure that whenever you figure out your probabilities, that like on spinners and stuff like that, that you have equal parts. So here's a spinner with 8 equal parts. So it's like tossing a die that has 8 sides to it. Same kind of concept. So you have 1 through 8. You're going to flip a coin and toss a spinner. And spin a spinner. The spinner is likely to land on each number equally. That means it's not weighted, it's a fair spinner. Use a tree diagram to find the probability of each event. So let's have you guys make a tree diagram. You're going to toss a coin. Let's toss a coin first. Then spin. So let's have you make a diagram. First of all, how many possibilities are there when you toss your coin? How many possibilities there on your spinner? So altogether, how many outcomes should we have? 16. Okay? So let me see you make your tree and give me your outcomes. Make your list of outcomes. Everybody should be doing this. With that one, everybody can draw a tree to do this. Then you're going to do your tails, 1 through 8. Okay, altogether we have 16 outcomes. So what is the probability? We're going to write it like this. And I want you to get used to writing your probabilities. Tossing a tail and spinning an odd number. So what is the probability of getting a tails, that's in this column, and it being odd? How many odds are there? 4. So what is the probability of getting a tails and making it odd? 4/16. I want this one, this one, this one, this one. 4 out of 16. Now, work with me for a second. What is the probability of getting tails in your spin? I'm sorry, in your flip. Just your flip. In your spin, what is the probability of getting an odd? A half. Isn't it the half odd, half even? 4 out of 8? Now when I multiply this, isn't that the same as this? And on your tree, can't you do your probabilities? Here's your tree. Heads, tails. Isn't this 1/2? 1/2? And aren't these, okay, all 1/8, 1/8? And then you got 3 of those, 4 of those all together, 4/16. Does it work out the same on your tree? I want you to be able to see these multiple ways. Okay, what is the probability of tossing a heads or spinning a number greater than 3? What numbers are greater than 3? Excuse me. Does it say or in the book too? Or spinning another greater than 3. Okay, so or is a little different. Excuse me. I'm going to get it in a head or a number greater than 3. So how many heads are there? I forgot what?
8.
Oh, 8. Sorry. Thank you. I forgot 8. Okay, a number greater than 3. How come I didn't count 3? Has to be greater than 3. So now let's count off my heads. I have 8 heads. So or a number greater than 3. I can't recount these because I already counted them. And so therefore, how many numbers are greater than 3? 1, 2, 3, 4, 5. So 8 and 5. 13 out of 16. You can't recount the ones you already counted. So a heads or a number greater than 3. 4, 5, 6, 7, 8. Oh, did I miss 8 again? 5. No, I didn't. I keep missing 8. Okay.
If you say
Yes.
and, you multiply them.
Well, yeah. If you say and, it means it has to happen at the same time. If you say or, you want them separate. You're going to give me heads or I'll take your tails on your spin. I'll take the odd numbers on your spin, regardless if it's tails or not. I'll just take the odd numbers or a head. Doesn't it give you more probabilities to get better chance? Right? It gives you a better chance because I'm going to kind of add them together. I don't want to do the add part, but we can certainly count them on your sample space, which is what we're kind of wanting you to do. I threw this in when I multiplied, but the add we're going to do a little bit differently. Find the probability of tossing a tail and spinning a number less than 6. What numbers are less than 6? Can I count 0? No, because it wasn't on my spinner. So again, if this is my and, find the probability of tossing a tail. I got to be in the tails column and a number less than 6. This has to happen at the same time. So which numbers are less than 6? 1, 2, 3, 4, and there's my T1 up there. 5 out of 16. You'll get to see the difference between the ands and the ors this way. Ors mean I want one or the other. Ands mean I want them at the same time. Okay? So that's what we're looking at there. All right. I think there's one more. Your college identification number. Your college identification number consists of 8 digits. So start like this. Start with 8. And each digit can be 0 through 9. And each digit can be repeated. What is the probability of getting your college identification number when randomly selecting or generating 8 digits? How many, think this out for a second. If you have a college identification number, much like your ID for school, how many ID numbers do you own? 1. Only one is assigned to you. So only one of these numbers is yours. This is the difference between probability and how many ways. In how many ways can I make a college identification number with 8 digits? This how. If I can repeat anything. 10, 10, 10. And what do I do with these? Do I add them or multiply them? Multiply them. If I added them, I wouldn't get too many different college numbers, would I? So I've got 10 to the 8th power. You could leave it scientific notation. That's how many different combinations you could get of these numbers. Because you're allowed to repeat. How many do you own? 1. So what is the probability out of all of these different ways? Do I select your college number? One way. 1 out of this. Is that probability large or small? Very small. So here's the difference. When they ask for the number of ways, they're asking for this number. When they ask for the probability, that's going to be your bottom number. You've got to do how many ways first. So therefore, it's very small. Now, I don't know if the book leaves it in scientific notation numbers or not, but you could leave yours, oh, they actually wrote the zeros out. You could leave it either way. And you'll be fine. Okay, here's another little one. A little bit of a spin-off on this one. Your college identification number now consists of 9 digits. So will we get more possibilities than we did with 8? Yes. Now, the first 2 digits of each number will be the last 2 digits of the year you are scheduled to graduate. The other digits can be any number 0 through 9. This has to be the year you graduate. So let's say you're just entering college today. This is the 2015. And in 4 years, you'll graduate in 2019 or 2020, whatever. You'll say you graduate in 2020. Those have to be 20, and these can be 0 through 9. And they can be repeated. So let's work on these guys first. How do I set this up? What would these be? How many possibilities do I have for these guys? 0 through 9, and I can repeat. 10, 10, and I'm going to multiply these. 10 to the 7. Now, what do I use for the first 2? I'm going to graduate in the year 2020. Ah, good. That number is not going to change. I need it to be a 2. I need it to be a 0. Good. Very good. So, how many different ways can I generate this? 10 to the 7, or add your 7 zeros, move your 7 zeros, and work it that way. If they ask what is the probability of getting your identification number, then it's 1 over that. See the difference? Kinda, sorta. Interested, not interested?